Stadium Monday night. They have been beaten tonight here in Atlanta. Panama coming from behind after the 18th minute. Temzee a red card and a U.S. lead that lasted 3 minutes 36 seconds. Pending Bolivia doing the U.S. a huge favor by pulling off a shocking result later tonight in New York. Let's send you back to Rob Stone in Los Angeles as it finishes. Panama 2, the United States 1.
John, Stu, thank you. Copa America 2024 tonight here on Fox is presented by Geico. A lot to get to here in the post-game show. The U.S. playing a much of this match, a man down against Panama. There's your winning strike. Jose Fajardo in the 83rd minute off of Ethan Horvath's hands. His 12th international goal, giving Panama the difference maker. They get the upset over the 11th ranked team in the world, the United States, 2-1. You go back to day 3, Ecuador. Remember, they went down a man, took a lead, ended up losing it 2-1 to Venezuela. Same story tonight in Atlanta. The U.S. goes down a man, takes the lead, and then gives it up. So much to talk about. We're going to get plenty of reaction from the manager, Greg Berhalter, and the players as soon as we can. Rob Stone, Clint Dempsey, Carly Lloyd, Alexia Lawless. Lex, your takeaways right now from this loss?
I mean, this one hurts, obviously. But there's a strange part of me that said, you know what? All chips in, all right? We talked so much about this tournament being an assessment of this team, an assessment of head coach Greg Berhalter relative to getting out of the group and playing against the likes of Colombia and Brazil. Well, you know what? That challenge and that assessment and that ultimate assessment is now going to happen in the third game against Uruguay. And they better be up for it. Because if they do not go through, Greg Berhalter is going to lose his job, and rightfully and fairly so. But this is a situation that this team, including Greg Berhalter, have created for themselves. Now, find a way to get out of it.
United States, Uruguay in Kansas City, Monday, July 1st, live on FS1. Clint, this was a tough watch, and that red card to Timothy Weah.
Alrighty. Welcome everyone to our second machine learning workshop. Today's going to be a really interesting one. We're going to build on some of the things we talked about on Tuesday. On Tuesday, as a reminder, we talked about the different categories of machine learning models. So we talked about the differences between reinforcement learning, unsupervised learning, supervised learning, semi-supervised learning, and we gave a really quick run through of fitting a decision tree model. Very, very basic. Well, we're going to extend that today. We're going to go even further and a little bit more in depth. We're going to talk more specifically about supervised learning today. As we talked about last time, that is the most important category of machine learning model. It's the most powerful. It's by and large what we're going to work with. So we're going to dive deeper into a couple of different subcategories within supervised learning to learn about that. Cigar, welcome. He says good evening. See, we've got others tuning in as well. Okay. As kind of like a small introduction to what we're going to do today, and a little bit of a story, I want to share with you this image. Okay. Oh, got to make it a little smaller. Okay. So this diagram is one of the ways of diagramming something called the CRISP-DM methodology. And now CRISP DM starts for the Cross-Industry Standard Process for Data Mining. And you might raise an eyebrow at that because no one has called data science data mining for like a decade or so, 15 years or so. Okay. But nonetheless, I feel like this diagram in particular, I particularly like. I feel like it gives a good overview of what it takes to follow a framework for fitting machine learning models. And you'll find yourself visiting each of these different steps and stages along the way. The first step here is business understanding. Usually you're doing machine learning in the context of your job, and you're trying to generate some value for a business. Maybe they want to increase sales. Maybe they want to increase the conversion rate on their marketing emails. Maybe they want to decrease customer churn, right? I mean, there's 1,000,001 different applications, but usually there is some larger goal, a business goal, that is driving your job and what you're trying to accomplish, right? So, and I like underneath these, it has some ideas of different tasks that might be involved in each of those stages of this process. Things like determining business objectives, assessing the situation, determine data mining goals, producing a project plan, etc. Those are ideas, right? And then after you know kind of what you're trying to do, you have to collect data. And you have to see, do we even have data that speaks to that particular business goal? And most of the time, the answer, honestly, is no, you don't. Having access to good and useful data is by far the biggest bottleneck that we have to making useful and valuable machine learning systems. Companies that are doing truly novel things with machine learning algorithms are usually doing it because they have access to some proprietary data set or a way to acquire data that nobody else has access to. The users on their platform are generating some kind of unique data, things like that. And in fact, this is one of the things I tell some of my students as they're looking for things like portfolio projects to do to impress employers, is to find data sets that no one else has access to. And I've seen students do things like take their fitness data off of their smartwatch and use their own personal fitness data, or track the number of hours they've slept each night and the amount of caffeine they've consumed the previous day, right? Like, and gone and collected truly novel and sometimes personal data to be able to do interesting things and have a portfolio project that is a little bit different than, you know, what else is out there, right? Well, then we get to the data preparation step. And the data preparation step is probably what takes the most of a data scientist, data analyst, data engineer's time, is getting that data ready. And this has a wide-ranging set of tasks, anything from preparing a database, surveys, pipelines, data pipelines to get the data from point A to point B, waiting on somebody in some other department at the company to give you access to certain data, waiting to get credentials, etc. There's all kinds of things, but cleaning data, most data scientists will tell you, takes upwards of 70% of the time they spend preparing data. Now, I took it easy a little bit. I took it easy on you a little bit on Tuesday. If you had a chance to look at the exercise that I shared on the Temzee website, the data set that I gave you that you were to try and to fit a decision tree model to, it's called the Palmer Penguins data set. I gave you a cleaned up version of that to make your life easier, to make the code a little bit more approachable. Today we're going to work with that data set again, but we're going to work with the not as clean version of it, and we're going to have to do some cleaning to it, so we're going to get a little of practicing. Cigar asks a really good question. He says, is that what data engineering people do, making data ready? And that is one of the ways that data engineering is defined. I've found that the description of the data engineering job title varies quite widely from company to company. At some companies, a data engineer is exactly what you said, Cigar. It's a person who tries to make the data scientist's job easier, so the data scientist can focus on the ins and outs of modeling, and the data engineer helps with setting up data pipelines, data cleaning, data integrity, all those kinds of things. But I've seen at other companies where a data engineer is more sewing together a whole bunch of databases and loose ends and data sources into one coherent, singular data store. And that's mostly their job, is just making sure that all the data is flowing in and the reports are being run at the right times and all those kinds of things. So it varies a little bit, but I'd say that the way you described it is a common way to break it down. So yeah, good question. After data preparation, we have modeling, and modeling is tricky. Modeling is the thing that people think is the fanciest and the coolest part of this whole process, but it is really just one of many different steps, right? Selecting your machine learning model, make sure you're doing all the things to make that machine learning model successful, and chasing that end all be all goal of generalizability, right? Training that model on data that we currently have, so that in the future it can do well on data that it hasn't seen before. And if it doesn't do well on data that it hasn't seen before, well, then it's not a good model, right? And so part of that process, we called that process validation, or model validation. That's similar to model evaluation, right? And we did something called a train test split on Tuesday as a very, I don't know if it's simple, but as a beginner's approach to doing model validation. And I'm going to show you a new tool that I didn't show you on Tuesday that might make your life a little bit easier if you're doing train test splits to validate basic machine learning models. So I'll bring that up when we get to it in our code portion. And then last but not least, there's model deployment. And model deployment is a whole ball of wax in and of itself. This is usually when a data scientist job starts to have some crossover and overlap with the team of software engineers, particularly back-end software engineers, who are probably building some kind of API, and you can export your model's weights and import it into a web server backend so that people can make queries to that API and get predictions back out. They'll send their data inputs into the API and they'll get their predictions back out. And there's all kinds of extra considerations to think about at that step. Sometimes models, over time, their predictions get worse and worse and worse and worse, as the data that comes into them is increasingly dissimilar to the data that the models were trained on. So models sometimes need to be retrained periodically. And sometimes new data is streaming into the model, and we want that model to be retrained very often. Sometimes some models have a limit to the amount of throughput, or the amount of data that can be passed through them at any given time. So you have to do things to be concerned about the loads that are being put on your API and the amount of demand for predictions that your model's being placed under, things like that. And there's a whole nother ball of wax there. So I really just wanted to go over this framework here, because if you needed a roadmap for a good way to approach data science, it would be to follow this path. And you'll notice here that there's a lot of backwards arrows in a few different places, because sometimes you hit roadblocks. Sometimes you hit frustrating things. For example, maybe you're at business understanding, you're like, oh, the business wants to do A, and then you go and you check your data availability and you're like, we don't have the data to do A. So we either need to change what our business goal is, or we need to refine our business goal, or maybe our business goal needs to change from fitting a cool machine learning model to shoring up our data collection or something like that, right? And that be the top priority for a period, right? And so each of these backwards arrows indicates places where things could go wrong, and things often do go wrong. For example, if you are doing model validation and your model's not generalizing well, it's doing okay on the training data set, but it's doing poor on your validation or test data set, that's called overfitting. And if your model's overfitting, you got to go back and you got to prepare your data a little bit better, or tune your model in some more specific ways. And there's some other things. There's a lot of techniques we can get to there about how to do those things. We're going to eat this elephant, one bite at a time, but a lot of cool things there. And then, yeah, so the story I was going to tell around this is that when I was in college, I wanted to learn data science, but I didn't know exactly how to put that into words. And so when I was at university, I took computer science courses and I took statistics courses, but there was nowhere on campus where I could learn Python for predictive modeling. I could learn a lot of linear regression, and I could learn that kind of statistics. I could learn R on campus, but I wasn't as interested in R. I wanted to do machine learning, but I didn't even really have those words for it yet because I was still trying to figure things out. I knew I needed some math, so I studied some math, some statistics and linear algebra. And I took some computer science classes, which mostly taught me building operating systems with Java. It was pretty outdated. And I wanted to build websites in JavaScript. I wanted to build APIs. I wanted to make predictive models. And there wasn't really any place to do that on campus. So I went to a mentor of mine and I said, here's kind of what I want to do. Like, how can I learn how to do this? And he said to me, it sounds like what you want to do is data mining. And I was like, data mining? Yuck. And what I didn't understand is that he and I, we just weren't speaking the same language. He was trying to say data science, but I'd never heard data science called data mining because it's a little bit of an outdated term nowadays. And you'll see that it says here the source is CRISP-DM 1.0 from crisp-dm.org. This website doesn't exist anymore, and CRISP-DM is not an industry standard anymore. But I still think it's not a bad framework. That's why I say somebody might raise an eyebrow at me showing this to you because they might see it as slightly outdated, but I don't think it's really very outdated at all, mostly just the terminology around it and the push to make this the industry standard is not as at the forefront of the industry anymore. But I really like this diagram and I think it'll serve you well. And I like this diagram specifically. Like if you Google CRISP DM, you're going to see all these much simpler circular ones, and I don't think they're as useful. All these circle ones. And they get across the idea that it's cyclical, but there's just not nearly as much detail, not as useful as this one. So that's why I'm sharing that one with you guys today. So last time we met, we really just did this modeling step barely, and we did this evaluation step barely. And that's all we did. Today, we're going to open things up a little bit more, and we're going to talk a little bit more about about data understanding. We're going to talk a little bit more about data preparation. Well, the modeling is going to be the same, but we're going to understand that model that we're using a lot better rather than just running the line of code and being like, well, it's trained. I don't know what it did or why it does what it does, but it said that it's making accurate predictions, right? We're going to understand it a little bit better. Do you have any questions for me before we jump into our next section of our discussion? Just checking the time. Okay, and if you are typing a question, keep on typing it. I will get to it. But so again, connecting with some of the things we talked about last time. Remember, we talked about how whether or not we can do supervised learning is driven by the presence of this target variable, the thing that we want to predict actually being included within our data set. Right? This target variable, or Y variable as we sometimes call it, is a little bit different and special compared to our other quote-unquote X variables, also called attributes or features of our unit of observation. Right? Well, I'm here to tell you that there's even some extra considerations we have to take based on our target variable that we didn't talk about last time. Within the category of supervised learning, there are two categories of algorithms. We have what are called regression algorithms and classification algorithms. And which of these we're doing, regression versus classification, depends on the nature of our target variable, right? So what is regression? Well, we're using regression algorithms whenever our Y variable, our target, is continuous. Now, continuous has a very specific meaning in mathematics. I want you to think more about just like the regular meaning of the word continuous. Forming an unbroken whole without interruption, right? In machine learning, we say that a target variable is continuous when the variable can take on any value within a certain range, right? Any value within a certain range. One great example of this is sale price, right? What value can the sale price take on? Well, it can take on $375,000 exactly, or it can take on $375,001 or $375,002, right? And we can get as fine-grained as we want to get, but it would be okay if the sale price took on any value from $0 to tens of millions, right? And there's so many different values it could take on there that we call this a continuous variable. In the mathematics sense, it might not be exactly continuous. It might be something that in the mathematics sense is actually semi-continuous, but it's still pretty darn continuous. It does not have a finite number of options for what we can predict. Because if it did have a finite number of options for what we could predict, well, then it would be what we call a classification algorithm, right? So classification is kind of the opposite. It's whenever we have what's called a discrete or categorical variable, when there is a finite number of options for what we can predict. Okay. Now, before we get a little bit more into classification, I want to clarify a few things. I want to clarify first that the category of regression algorithms is different from linear regression. Okay. It's not the same thing as linear regression. Linear regression is one specific algorithm. Regression is an entire category of algorithms. And mixing those two things up is one of the fastest ways to embarrass yourself in a job interview. Okay? That's why I bring it up. The reason why linear regression is called linear regression is because the guy who invented it, Francis Galton, sometime in the late 1800s, he was studying the relationship between the height of parents and the height of their children, right? And this is the graph, I think, from one of his publications. Okay, if I make that a little bit bigger. And this is like a very old school version of a scatter plot. You can see the y-axis is parents' height, x-axis is their height of their children when they're adults in inches, right? And then instead of putting dots on this plot as if it was a scatter plot, in each of these quadrants he put the number of people that fell into that quadrant between 68 and 69 inches for the child and 69 and 70, right? And so you can see that we have much bigger numbers here in the middle. And he noticed that, this shape kind of forms kind of a cloud of data points, this kind of oblong ellipse or oval of data points. And it was kind of slanted. And he thought, hey, what if I fit a line along the long axis of that oval? We call that the line of best fit, and that's what a linear regression line is. But he called it regression because he observed that there was regression to the mean in the heights of children compared to adults, right? What does that mean, regression to the mean? Well, it means that even if your parents were really tall, it was likely that children were closer to the mean than their outlier parents, right? And opposite was true if you were really short. If you had really short parents, it was likely that you were, the next generation was closer to the mean. The next generation was taller than their short parents. So if you had parents that were really on extremes of the distribution, it was likely that their children were a little bit closer to the mean on average, right? We call that regression to the mean, that in each subsequent period, the next period is a little bit closer to the mean than the previous period, right? And so that line of best fit idea caught on and was called linear regression. This is how we think of linear regression a little bit more nowadays, right? A cloud of points, we fit a line of best fit to it. And we can talk about linear regression in coming days if you would like to, but that is the difference. So don't confuse linear regression and regression algorithms. Regression algorithms are just outputting a number that can take on any value in a range, arbitrarily specific. Classification algorithms are outputting a specific category or class, a classification, right? So I kind of have a little bit of a trick question for you. Are these following variables, should they be viewed as being continuous or discrete? A person's age, month of the year, person's height, person's weight, the temperature outside, the duration of a YouTube machine learning live stream, or liters, well, liters of what? Liters of water in an Olympic-sized swimming pool. I don't know, right? Should these variables be recorded as discrete values, categorical values, or as continuous values? Cigar says discrete. It says specific values on a range. And I want to tell you that you're right. But if you had said continuous, you would also be right. Because it's up to you, the data scientist, how you want to treat these. I want you to think about age, right? We typically take a person's age and we round down to the number of complete years a person has lived. But am I 32 years old? No, I'm 32.4769827 years old. But we don't talk about it that way. We round down to these discrete bins. We bin, I don't know if you thought about that, but we're taking a continuous age variable, and because it's too annoying to talk about all the decimal places, we're rounding it down into these discrete bins of 12-month periods, right? Same with month of the year. Could do the same thing. Do we want to talk about specifically the point in time, or do we just want to round it out sometime in June, right? A person's height. How many decimal places do we want to include? Or are we just going to round to the nearest inch or the nearest centimeter? Oh, didn't mean to double click on that. Same with weight, temperature, duration, liters, right? And a lot of this really depends on what exactly it is that we're measuring. But with many of these variables, we as the data scientists, we ultimately get to choose, am I going to treat this as a categorical variable or as a continuous variable? And it really depends on how many bins do we have. If we have like 10 different values, then I might treat it as categorical. If I have 1,000 different values, and that's getting a little bit trickier. I probably want to treat it as something continuous if I can. Cigar says, so that means any discrete data can be treated as continuous if we want to. If we have enough of it, if we have enough different discrete categories and those categories are represented numerically, then yes. Here's an example of a discrete category that could not be represented numerically. Well, I need a big caveat on that, but here's the example. Something like eye color. Imagine you're recording things about people in a data set, and each row of your data set is a different person. One of those columns is eye color. First off, eye color really varies from person to person. It can even vary based on the kind of medication you're taking or whether you're like out in the sun or not. But usually we break it down, you know, if you're on your driver's license or your identification, you just say blue, brown, green, I don't know, hazel, something like that. And those categories in and of themselves are bins. But eye color has no inherent numeric value to it. Is green eye color more than brown? Or is brown more than green? No, they're just values, right? And so it can be tricky to translate that into a categorical variable. It can be tricky to transform that into a continuous numeric variable. I can just say, hey, in my data set, if it says blue eyes, make that a 1. And if that says green eyes, make that a 2. And if it says brown eyes, make that a 3. And we can end up doing that. We can just replace those string values with numbers. In fact, we're going to do that today with the data set we're going to work with. But that doesn't make it continuous. It will make it numeric, but it won't make it continuous. However, I would say, Cigar, that the opposite of your statement, that can we make any continuous variable discrete? Yes, we absolutely can through the process of binning. And just one example of that is shown here by this map. Heat maps like this, they get a funny name. They're called choropleths, C-H-O-R-O-P-L-E-T-H. So if you want to figure out the Python code to make a cool map like this, Google choropleth, and it will you'll get some tutorials on it, right? But the unemployment rate, it's not discrete, it's continuous. It could take on any value. But in order to make the heat maps colors more stark, we've binned them into these 6 different bins, and we've assigned each of these bins a color, right? So this is an example of taking a continuous variable, dividing it into these 6 ranges, smaller ranges, we call them bins, and then using that to display our data because it makes the data a little bit more digestible. So, yeah, okay, so this has been a long discussion about essentially a basic topic. Is it a variable that can take on lots of different values, or is it a variable that can take on just a few values? And if it can take on just a few values, we're going to use a classification algorithm. If it can take on lots of numeric values, pretty much arbitrarily many numeric values, we'll use what's called a regression algorithm. Okay. So today we're going to do some classification specifically. We're doing supervised learning, and we're going to use one of my favorite data sets. This is called the Palmer Penguins data set. Okay? And the Palmer Penguins data set is called that because it was, if I open this image here, collected by scientists at the Palmer Station in Antarctica. Okay? And the scientists at Palmer Station, which is here on the Antarctic Peninsula, kind of in the northwest of Antarctica, went to 3 different islands: Dream Island, Torgerson Island, and Biscoe Point. And they took measurements of the penguins that they found there. Grab a penguin and weigh it and measure its flippers and its bill. And they put it in a data set. And I happen to have a slight curiosity with birds and penguins in general. Okay? In fact, I'll show you this here. Where did I put it? I went to my local aquarium where they have Gen 2 penguins, and I paid a silly amount of money to be able to feed the penguins. So this is a video. Let's see if I can make it full screen. This is a video of me feeding Gen 2 penguins at the aquarium. My daughter. It was pretty sweet.
They like you, Maggie. Look, he's gonna eat your fish.
They are the fastest swimming penguins.
Good job.
But they're kind of a regular size, right? So this is a diagram that was actually on the wall of that aquarium, and it can give you an idea about the relative sizes. So there are 3 different species of penguins that are included in this data set are Adelie penguins, chinstrap penguins, and Gen 2 penguins. Okay? And you'll notice that Gen 2 penguins are a little bit larger on average than chinstrap and Adelie. I don't know if this Adelie penguin is standing straight up, but Adelie and chinstrap are about the same size. And you'll notice that visually, it's probably pretty easy to classify them, right? If I see a penguin with a chin strap, well, then it's a chin strap penguin, right? Gen 2s and Adelies might be a little bit harder to tell apart, but visually, not too hard to classify them. Well, what if we didn't have a visual marker? What if we only had, sorry, pardon my scrolling. I'm trying to get to the right area here, because I'm going to load the data set here and show you what it looks like. I just want to make sure I'm doing that in the right code cell. Okay, so I'm going to load this data set. We're going to import pandas. Oh, wait, before I do that, sorry, before I write code, I realized I made a slight mistake last time, and that I meant to share with you a blank version of this notebook, which means I needed to make a copy of it. Okay, so this is, I'm going to call this the student version. And this one will always be blank. So if you want to follow along with me, which by the way, I would encourage, the more you get your fingers on the keyboard, typing, the more the code syntax will get into your brain. Okay, so this is a blank version that you should be able to then view, and then you'll have to come and say File, Save a Copy, and Drive, and then you'll be able to follow along with me should you choose to do so. And I'll put a link to that in the video description as well for anyone who views this after the fact. Okay, and I wanted to make sure I did that before I wrote any code here. Goodness, I'm being long-winded today. We gotta get going. And if we don't finish this, we can continue on with this discussion on Tuesday of next week as well. Okay, so I have a CSV on GitHub of this data set. You can find it in a lot of different places. I will share this CSV with the link to this as well, because I realize it's kind of a lot to type out, but that is the link to the CSV on GitHub. And let me know if you need me to make my font bigger. I'll try and do that without you prompting me. The stream here is not very high definition because my computer's not very good. So I'll try and make the font extra big. Hopefully that makes it more readable. Okay, so here's the information we have. We have the species of penguin, the island it was found on, the bill length of the penguin in millimeters, the bill depth in millimeters, the flipper length in millimeters, the body mass of the penguin in grams, and the biological sex of the penguin, be it male or female. And that's all we have. Given the species column, if that is our target, okay, the rest of these are then our features or attributes. The rest of these are our x variables. Can we use those x variables to accurately predict the species of the penguin? And one of the first things I want to show you is, if we look at that species column and we do value counts, okay, value counts is going to show us the different values in that column, and it's going to show us how many of each of those different values there is. So we have 152 Adelie penguins, 124 Gen 2 penguins, and 68 chinstrap penguins. And those are the only three values that this y variable can take on. And that's what makes this a classification task. We're trying to classify each of these penguins as being of one of those three species. Okay. The next thing I want to show you is I just want to show you the islands. Biscoe, Dream, and Torgerson. Okay. Most of the penguins were seen on Biscoe Island. And is there something else I wanted to show you here? Oh, let's also look at how many males and females. Okay, so it's about 50-50. 168 males and 165 females. So the reason why I tell you this about the penguins and about the islands and such is I hope that gives us a little bit more context for this data. Maybe makes it come alive a little bit more, makes it a little bit more interesting. I'm going to remove this code, so I don't think we need it anymore. Okay. So that is a very first look at the data. Okay. I'm going to add to our discussion of last time. We're going to talk about data preparation for the first time, right? Going back to our CRISP-DM methodology, right? We've worked a little bit on data understanding, getting some context for this data about penguins and where it comes from. Now we're going to talk about data preparation. And when we are doing machine learning, there is always a minimum of 2 data preparation steps that we have to do. Always. Always. Okay? We have to check to make sure that our data does not have any missing values. There's no missing data. And all of our data must be numeric. Okay? Now there's a slight exception to this. Sometimes, depending on the algorithm, our y variable, our target, doesn't have to be numeric. But usually we make it numeric anyway. For part of our discussion today, I'm going to leave our y variable as the literal written out species, the strings for each penguin, and then later on we're going to make it numeric. Okay? But you'll notice that we have some x variables that are not numeric, like sex is recorded as male, female, it's the written out word. And island is the written out word. We're going to have to take each of those 2 columns and turn them into numbers. At the end of the day, these algorithms, they're just number crunchers. So they can't do their jobs unless they're given numbers. The next thing I want you to notice is this fourth row here has this funky word in it, nan, which in some programming languages stands for not a number, but this is the Python package NumPy. It's the way that NumPy represents a bad or a null or a missing value. Okay, so this is one example of a null value. So that means for this particular penguin on Torgerson Island, they saw that it was an Adelie penguin, but maybe they grabbed it and then it wriggled away and it ran off and it jumped into the water, and then they couldn't record anything else about it. All right, so they know it was an Adelie, they know it was on Torgerson, but they weren't able to capture any of the other pieces of information about it. Well, we can check for null values throughout our entire data set with this line of code. df.isNull.sum. So df, what the isNull function does is it looks through every single cell and it says, well, if it's a null value, put true. If it's not a null value, put false. And then what sum does is it sums up the number of true values in each column. So essentially, we're summing up the number of null values by column. Okay? And we notice that sex has 11 missing values. And then bill length, bill depth, flipper length, body mass, those have 2 missing values. Okay? And we need to deal with this. We cannot leave any missing data in our data set, or we're not going to be able to run it through our machine learning algorithm. Okay? Let me readjust Windows slightly so that I can. All right. So here's what we're going to do. I have a suspicion that, oh, I scrolled too far. That, see all these nans? They're all on the same row, right? They're all with the same penguin. And I bet that we have 2 penguins that are in this same situation. That's why we have 2, 2, 2, 2. So I bet there was 2 penguins where we recorded the species and the island, but nothing else about it. And then these 11 other penguins, I don't know how easy it is to tell the sex of a penguin, but I imagine it was tough and maybe they got away and didn't like being investigated, things like that. But I think there's a little bit of a different situation between those 2 sets of missing values. So I'm going to treat them a little bit differently. I'm going to do something called imputation, or I'm going to impute the sex column, because if I have a penguin where I'm just missing the sex, but I have all the other pieces of information, well, I don't want to lose those other pieces of information by dropping that row or removing that row. So I'm going to fill in the sex, but I'm going to want to keep the rest of the values. So I'm actually going to make up a value to put in for the missing values on this column. I'm going to insert my own value. And that might feel like we're breaking some rules, but it's not. As long as our model still generalizes well to unseen data, I can do whatever I want. Right? So because this is just such a small portion of my data that's missing, I am okay to just fill these in so that my machine learning model can work on them. Okay? And there's a lot of ways I can do this. Here's how I'm going to do it for today. Oh, goodness. I'm going to grab that column, and I'm going to say, hey, pandas, please fill the NA values. That's another way. You'll hear nans called NA values. NA standing for not applicable or not available. And in a lot of data sets, if they're written by hand, a person will write NA, right, if that question was not applicable or something like that. So for that reason, these null values are also called nans, and they're also called NA values. There's lots of different names for them. Okay. We're going to fill those, and we're going to fill them with a specific value, and I'm just going to fill them with male. Okay. And the reason why I'm doing that is because male was the most often value here. So is this the best, most perfect reproduction of the original data? Probably not. But is it the most terrible thing I could do either? Also, probably not. It's somewhere in between good and bad. But I have to do something. I can't leave these null values as is. So if I fill those in, now there are no missing values in the sex column. Okay. The next thing I'm going to do is I am going to, these two rows that have missing values everywhere else, I'm just going to drop the entire row. So I'm going to go from having information about 344 penguins down to information about 342 penguins. And because that's less than 1% of my data set, I'll be okay to do that. In fact, I would probably be okay to do that if it was less than 10% of my data set, as a rule of thumb. Not a perfect rule, but an okay one. So we're going to use the drop NA function, and we're going to override or overwrite the original data set here. And we should have 342 penguins now, and we do. And that row that had the NA, the NaN values in here is now gone. It's been deleted. Okay. So that addresses the null values. And I think I have a lot of extra code cells here. Now, final check for null values, df.isNull.sum, and we should see all zeros, and that means we're good to go. Okay? So that is null values addressed. The next thing we need to talk about is taking these categorical values and turning them into a numeric representation. And we're going to do this in the very basic way I talked about, where we're just going to look at the island value. And whichever one of these values is the most common, Bisco, we're going to replace Bisco with 0. And whichever one is the second most common, Dream, we're going to replace Dream with 1. And the third most common, we're going to replace with 2. So we're really just going to switch out the names of the islands for the numbers 0, 1, and 2. And there are a lot of ways to do this. Because we're short on time, I'm just going to show you 2 of my favorite ways to do this. Okay, we're going to say df island, and we're going to call this function called replace. And then we can pass replace a dictionary where we give it the old value and then the new value you want it to be replaced with. So like Bisco, I want to be replaced with 0. And Dream, I want to be replaced with 1. And Torgerson, I want to be replaced with 2. And it says Torgerson, oh, I got to make this a string. There we go. So this is the new column, just like that. Another kind of crazier way that's a little bit more confusing is using something called category codes. Okay. So to do that, I will take the island, and I'm going to do what's called casting it. I'm going to change its data type. Right now, all the values in here are a string, and I'm going to change its data type to something called a category, which is a weird pandas-specific data type. But here's the thing. When I cast something to a category, it automatically assigns to each of the categories, to each of the different values in that column, something called a category code. And it just so happens that the category codes match exactly what I just did. Whatever category is the most common will be assigned the category code of 0. Second most common will be given a category code of 1. Third most common will be given a category code of 2, etc. Right? So I'm going to say as type category. That's me casting that column to a category, and that's what gets the category codes assigned. And then I'm going to look up those category codes and save them over the original column. And this does exactly the same thing as dot replace right here. But with dot replace, I had to go and look up each of these values and type them out one by one. If I had 40 different categories, it would be really a big pain to type each of those out in a dot replace function. If I had 40 values, this would be the same line of code here. So if I have a lot of categories, this is definitely less typing, but they do the same thing. So island should now be replaced with numeric values. Excuse me. Oh, Cigar asked a really good question. If we already replaced island, then how will it have a category? So right here, I actually did not replace it yet. Okay, because this is just me saying, hey, what would this column look like if I did replace its values? I didn't save over the original column until I do this. Right? So adding this to the front says, hey, make the changes and then save over the old column. But if I don't leave this on, then it shows me what it would do, but doesn't actually go and make the changes quite yet. Okay, so this is kind of like a preview. But once I save over the original, then that's when the change actually takes place in my data frame. Really good question. There's something else I could say, but I'm not going to get into it yet. So yeah, that's the difference. I'm not overriding the original column yet. I also need to do this to the sex column as well. So let's just add another code cell here, and we'll just change the header here. And it should assign 0 to male and 1 to female. That's just because there happens to be more males than females in our data set. And there we go. Okay. Now everything except for the y variable is numeric. We've removed missing values and we've made all of our features numeric. Those are the bare minimum data preparation steps we have to do before we do any machine learning algorithm. Excuse me if my voice is funny. I've had a little bit of a cold, but alrighty. Okay. I'm going to delete these code cells because I've been simplifying things as we go along for time's sake. So I don't need as many of these as I thought we would need. Okay. Oh, you know what? I did need some of those columns, some of those code cells. I'll put them back in. Okay. The next thing I want to show you is that usually before we go and we fit a machine learning model, we usually try and understand our data a little bit better. We usually do something called exploratory data analysis, and I'm going to do a little bit of that with you here today. Okay. What we're going to do together is we're going to make some graphs. And we need to make these graphs because I'm going to refer back to them frequently as we talk about what the decision tree is doing to make its predictions. They're going to really help us understand what decision trees do. Okay. So we're going to use a Python package called Seaborn. Comes pre-installed in Google Colab. We just need to import it. And you can import it as whatever you want. You can import it as bananas if you want, but everyone calls it SNS. So that's what we'll do too. Okay. And then the first kind of plot we're going to create is one of my absolute favorites. It's one called a pair plot. And Seaborn makes this really, really easy. Because we've already done all the work to make our data numeric, we can just pass it our data frame, and then this hue should correspond to our categorical y variable column header. So the column header for our species column is species. And that's all the code I need to write. And I'll get a really cool graph. This graph is complex, so it's going to take it 15 seconds to render. But then I'll be able to show it to you. And I think you'll go, ooh, ah, once it appears. Here we go. All right. So this is a pair plot. And what a pair plot is it takes all of our columns and it plots them against each other. So you'll see we've got island, bill length, bill depth, flipper length, etc., body mass. Make this a little smaller. And sex. And then on the x-axis, we have those same things repeated. So whenever we have a column that meets up with itself along the main diagonal here, we just get a histogram of it. A histogram of it, right? So this is well, the island columns are not very useful. I think what's most useful is the more continuous variables, the bill length, bill depth, etc. Right? And they're color coded by species. That's what the hue parameter does. So we see that yellow is our Gen 2 penguins, blue is Adelie, and green is chinstrap. And just by looking at these scatter plots, I think it's easy to see that Gen 2 penguins are a little bit more different from the other two, right? They're usually off here on their own group, whereas the Adelie and Chinstrap, they're closer together, meaning that the Gen 2 penguins' measurements are a little bit more extreme, a little bit more different than Adelie and Chinstrap. Adelie and Chinstrap tend to be closer to the same size, but Gen 2s are bigger, right? Body mass for Gen 2s is higher, and then Adelie and Chinstraps are about the same size of penguins, right? So there's so many cool and interesting things we can glean from these graphs once we stare at it for a little while. These graphs on the main diagonal are a type of smoothed out histogram. They're called a kernel density estimate, or a KDE is the abbreviation. And we'll see these again in another minute, because I want to take each of these kernel density estimates and I want to blow them up a little bit bigger to look at them a little bit more closely. And we're going to use something called a hist plot to do exactly that. Okay. And with this hist plot, we're just going to look at the continuous variables: the bill length, flipper length, bill depth, and body mass. Okay. So I'll let the autocomplete work here for me. So there's flipper length. There's body mass. Okay. Did we already do bill length? We didn't do bill length. Okay. And we got one more. Bill depth. Okay. And you can see we have the same color coding going on, but where there's an overlap, right, of the histograms, right? It's like we've taken them and layered them on top of each other. The colors kind of blend together. So some of the histograms are allowed to be kind of behind each other. They're like opaque. So we have yellow, green, and blue, but where green and blue overlap, we get kind of this blue-green. Does that make sense, what we're looking at here? Another thing I want to do is I want to increase the bins, the number of bins. You're going to see what happens as I'm going to make the bins 20 here. It just makes it so the histogram has to take up more bars. We get a little bit more detail. So I'm going to add that to each of these as well. All right. Okay. So we're going to refer back to these graphs. You'll see that Gen 2 penguins have less deep bills, that Adelie penguins have shorter bills on average. Gen 2s are bigger, way more, and Gen 2s have a longer flipper length. Okay. So we can already see that there is some information in this data that can help us classify them, right? That's our end goal, is to be able to say, oh, well, it's a penguin that weighs 6,000 grams. Oh, that's got to be a Gen 2 penguin, right? And be able to make those accurate predictions and have those predictions be informed based on these distributions. Okay. And that is basically what our decision tree model is doing. Is it's looking at these distributions and saying, which of these could I use to really isolate one of these species? It goes, oh, well, it looks like Gen 2 penguins are really different in their body mass. So what if any penguin above 4,700 grams I said was Gen 2? Bam, classified. That's my prediction, right? And then with the penguins that are left over, the ones that it hasn't isolated as Gen 2, it's got to find some other way to differentiate between them using one of the other columns. And that's, in a simplified version, what our decision tree model is doing. And look at all these code cells I have left. I think we're going to have to continue to talk about this more on Tuesday as well, because we only have a few minutes left. Okay. I know what we're going to do. So we're going to talk about the importance of starting any modeling process with something we call a baseline. And then we're going to improve upon that baseline in a way that's very similar to what a decision tree would do. Okay? So when I say to start with a baseline, I mean we want to make the dumbest useful prediction possible. Okay? So if we just look at the species column, yet again, we see that Adelie penguins are the majority of all of our penguins. Well, not the majority, but they're the most common species, right? So if I just said that those 151 Adelie penguins, let's see, what was my df.shape again? So I have a total of 342 penguins. That means that 44% of all of my penguins are Adelie penguins. Okay. Now here's the dumbest model that I can think of that is not technically a purposely bad model. And here's the model. The model is, let's predict that every single penguin is an Adelie penguin no matter what. If I did that, how often would my model be correct? Well, Cigar says 50% of the time. Well, it would be correct 44.1520467 whatever time. So about 44% of the time. Assuming that the penguins I see in the future, assuming that I view them in the same proportion as I'm seeing these penguins, right? If this is like if these numbers are relative to the general population, if they're reflective of the population numbers of the penguins I'm going to be running into in future scenarios, then my model is going to be right 44% of the time. Okay. Now that's not a good model, but any improvement on 44% means that my model must have learned something, right? That baseline is a dumb baseline. It's a baseline that hasn't taken into account really any information yet. So if I get a prediction accuracy, classification accuracy that is higher than 44%, that must mean I'm onto something. If I get an accuracy that is less than 44%, that means something has gone terribly wrong. Terribly wrong. And I need to like check for bugs and typos and make sure my computer hasn't crashed. Like less than 44 is absolutely unacceptable. We ought to be able to sneeze and do better than 44%. But it's just a starting place. Just a starting place. Okay? So here's what I want to do with you. I want to beat this 44% in the simplest way I possibly can. Okay? And we're going to do that by using a threshold or a heuristic, right? We're going to pick a cutoff point and we're going to say, hey, every penguin below that or above that is X species of penguin. Okay? But we don't want that penguin to be an Adelie penguin because that's already what we're predicting. So we need to find some way to identify Gen 2 or chin strap penguins. Okay. And let's just use flipper length because it looks like Gen 2s are a lot more different than the other ones in their flipper length. Okay. If you wanted to isolate the Gen 2 penguins, most of the time, what do you think would be a good cutoff to pick? Right? A value where we say, oh, above that value, it's really likely that they're a Gen 2 penguin. What number would you pick? And this is subjective. There's no exact right or wrong answer here. So guys, somewhere between 200 and 210? I agree, somewhere in here. I would maybe do like 206 because they got a pretty low yellow box right there. So let's say if it's greater than 206 in flipper length, then it's Gen 2. Otherwise, it's Adelie. We're never even going to predict chin strap penguins. Okay? But that means we've been informed by the data at least somewhat. Right? The data is telling us something about the relationship between flipper length and penguin species, right? And that's what we're trying to model. That's what we're trying to capture, right? So here's what we're going to do. I'm going to write a for loop, which is not something we do as often as you might think. At least a plain vanilla for loop is not something we do super often in data science. We iterate over things all the time, but we usually have other tools that do this for us. So I'm going to say for row in df.iterRows, and I just want to show you what each of these rows looks like. And to really make it clear, I'll put some extra dividers above and below it. Okay. So each of these rows is getting printed out one by one. And if I grab specifically the flipper length in millimeters from that row, let's see. Maybe I need to do it numerically. So if I grab the second value. It's not liking any of these. Oh, it's a tuple. Okay. So I knew that because it said tuple object, has no attribute. So what it means is that each of these rows, oh, and you can tell here because of the parentheses, has just two values. So if I say row 0, yeah, then that is just the row index. This is the first item in the tuple. Okay, we probably haven't talked about tuples. And then here's row, the second item. So we had the row in the index was the first value, and then everything else was the second value. And that must have been why I couldn't get at what I wanted to get at. Oh, goodness me. The output of this code cell is so long, I'm having to scroll so much to get back up to my code. It's one of the downsides of printing things out in for loops. Okay. So what if I say row 1, and then I grab flipper length in millimeters? There we go. So now I'm seeing each of the flipper lengths outputted, right? Because they're all around 200, give or take. Okay. So now I know I am getting at the flipper length of the penguins. And here's what I'm going to do. I'm going to write an if statement. I'm going to say if that penguin's flipper length is greater than 206, that's the value we settled on, then we're going to well, we're going to have a new list, and this list is going to be called our predictions. It's just going to be blank. We're going to append gen 2. Right? So if the penguin's flipper length is greater than 206, we're going to put gen 2 in here. Otherwise, we're just going to put a deli. Right? Because predicting every single penguin is a deli, that was our baseline. And now we're getting a little bit informed from the data, and we're saying, okay, predict that everything's a deli, but if its flipper length is greater than 106, predict gen 2. Okay. And here's what I end up with. A deli, 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 a deli. Am I gonna? Oh, and then it switches to gen 2. Gen 2, gen 2, gen 2, gen 2. Okay. And then back to a deli. Okay. Now the question is, have we beat our baseline? Have we improved upon our baseline at all? And in order to do this, we're going to have to kind of manually grade our predictions. So we have our list of predictions, and we also have the list of the original species. I'm going to cast this to a list. Okay. And now I need to compare these two. In fact, maybe I want to make both of these a NumPy array, which we can talk about later on. NumPy array is basically the same thing as a list, but it's got a couple of extra bonus features. And I need to import NumPy to be able to do this. Okay, and it wraps a little bit better. It's a little bit easier to read. Here's our predictions given just our one heuristic. And I think I say dot values, and I'll get a NumPy array here. Oh, I don't think I need parentheses. There we go. Now I want to compare them. Okay? And here's how I'm going to do that. I'm going to just, well, compare them. I'm going to check to see if they're equal to each other. Now the question is, can I do this? Can I compare an array of values to another array of values and ask if they're equal? Well, they're definitely, the arrays themselves are not equal. That's for sure. But because these are not regular lists, these are NumPy arrays, this prediction is going to happen element-wise. So that means it's going to compare the first item in predictions to the first item in our actual column. And then it's going to compare the second item to the second item, the third item to the third item, so on. So it's pairing them up. Each of our predictions is getting paired up with the true value. And it is a whole bunch of trues and falses. True is where we made the correct prediction. False is where we made the wrong prediction. Okay? And I think, let's see, if I do this, can I sum it up? Yeah. So this is the number of correct predictions. If I want the percentage of correct predictions, I need to divide that by 342, because that is the number of penguins we were working with, right? Now I am 79.2% accurate. All that I did was make the very simple observation that Gen 2 penguins have longer flippers, and I picked a cutoff, right? And my accuracy jumped from 44% to almost 80%. A simple observation, right? Well, our decision tree model, it is trying to do this in an automated way. It's trying to look at each of these and pick different cutoffs. And as it picks those cutoffs, it sees, okay, how much better do the predictions get? And the way that it does that is it tries to look at the purity of the predictions above or below that cutoff, right? So at our cutoff here of 206, above that, we had pretty high purity. Almost all of those observations were Gen 2 penguins. So that was a good cutoff, right? And the decision tree algorithm is trying every single different potential cutoff we could have in our whole data set, and it's measuring that purity at each different cutoff and using that to build a tree and to be able to differentiate these penguins. So I have a lot of stuff here to still talk about decision trees, but we are well past an hour. So what I think is I'm going to do two things. I'm going to share with you a completed version of this notebook that I made up earlier in case you want to look ahead, in case you just you can't wait to see some of the things I was going to show you with decision trees. We fit a decision tree model and we make some cool visualizations. Hey, check this out. Flipper length, 207.5. That was the very first cutoff that our decision tree made. Pretty darn close to what we chose, right? But then it continues, right? It's got these almost completely Gen 2 penguins that it's isolated, but it still has to figure out which ones of those are actually not Gen 2, which ones are Adelian chin strap. And then over here, it's got all the Adelian chin straps left, and it's got to figure out, all right, how do I discern between the Adelian chin straps? Well, it turns out that the island they're found on is a pretty good differentiator, right? And it goes down, breaking it down, and the decision tree's goal is to find these different cutoffs, these different thresholds, where it can keep on dividing and subdividing the data set further and further until we end at what we call pure leaf nodes. Each of these at the end is a set of penguins that is all of the same species. And it'll keep on breaking and using more and more cutoffs and thresholds and splitting the data set until every single penguin falls into one of these exact categories. And we'll talk more about the math, about how does it quantify what a good cutoff is, and some of those things a little bit more on Tuesday. So yeah, we have that to look forward to. I thought we would get there today. Turns out we won't. But that's why we're doing this every Tuesday and Thursday night, is so if we end up biting off more than we can chew, or if we end up having good discussion, we can just continue talking about it. Before I let you guys go, anyone who's listening to me right now, I want to ask you, are there any specific topics that you wish you could learn about in the machine learning data science space? Because I want to take your suggestions into account for what we talk about in the future. Would it be helpful if we talked about, reviewed some Python fundamentals? Would it be helpful if we talked about linear regression? Or do you want to get into the, into the weeds with large language models or neural networks, fancy stuff? Like, what do you think is going to be the most useful to you? If you have any ideas, please let me know in the chat. We don't have a ton of viewers on right now, so I will also blast out an email to everyone. Caesar says he wants to do more statistics and linear algebra. Okay, we could definitely do that. That's a good idea. I think I've always wanted to create material that is like a linear algebra course, but only teaching it through applied data science, because there's so much cool stuff with linear algebra. Haley says, could we review time series models? Ooh, time series models can be really tricky. There's a lot of specific peculiarities to time series models. Those are both good ideas. Caesar says, what related to data science? What not related to data science? So is that question in referring to linear algebra? Particularly in a lot of natural language processing, there's a lot of it, but like linear algebra is all about grids of numbers. And that's all tabular data is grids of numbers. Oh, gotcha. She says, I meant in my comment above. Yeah, statistics and linear algebra related to data science. Yeah, absolutely. I think we could do some really cool stuff there. I always think that while it is useful to just, go take a statistics 101 course or linear algebra 101 course, learning about those things in the context of like doing something cool with it, with code and with like making cool predictions, makes it just so much more interesting. So he says, agreed, statistics, please. Okay. Okay. So we'll meet again on Tuesday of next week. We're not going to meet on Thursday of next week because that is the 4th of July in the United States, and I will be busy with family stuff. So we're going to take a break Thursday of next week, but we will still meet Tuesday, and then the following week we'll go back to our regular Tuesday, Thursday schedule. Does that work okay? I mean, cool. Thank you for your good ideas. Thank you for participation. I hope this is not too basic for you guys. I hope it's useful to you, and I think we're gonna get to some really cool stuff in the coming days and weeks. So thank you for coming. I hope you please keep on coming, and we'll keep on delving deeper and deeper, peeling the layers of the onion back. So Okay, thank you, everyone. I won't take any more of your time. Have a great rest of your Thursday evening.